All right, so this week's paper is on characterizing and optimizing remote persistent memory with RDMA and NVM. The paper is by Xingda Wei, Xiaoting, and Xiaoting Xie, with help from their faculty advisors Rong Chen, Haibo Chen, and Binyu Zhang. And my name is Brian Luger, and I'll be presenting their paper. So the paper conducts a study to summarize the optimization hints that the system designer can use to exploit NVM with RDMA better. Specifically, they demonstrate how system configurations, NVM access patterns, and RDMA-Aware Optimizations affect the efficacy of RDMA and NVM systems. They then implement those optimizations into existing RDMA-capable systems, namely a distributed database called DRTM plus H and a distributed file system called Octopus. Both of these systems are designed with no production NVM that is available, and neither of them achieve good comparative performance using NVM. So using the optimizations detailed in the paper, the authors are able to achieve 1.2 to 2.4 times better performance. First, just kind of go over the agenda. We'll talk briefly about the contributions the authors claim the paper is making. I'll then go over a bit of background from the paper and talk about the author's testbed methodology before jumping into each of the optimization hints and ending with the benchmarks from applying the optimizations to the DRTM plus H and Octopus systems. Okay, so this paper conducts a thorough systematic study of how best to utilize NVM with RDMA with an explicit focus on remote write, where the client issues a remote write to the server NVM, either using one-sided or two-sided RDMA. The author summarizes the contributions from the paper as a summary of optimization hints, referenced later as H1 through H9, to best utilize NVM with RDMA, and an end-to-end study of improved RDMA and NVM system designs. To start with a bit of background, this is figure 1 from the paper. It shows the typical hardware components of a node with NVM in an RDMA-capable cluster. First thing to note is the RDMA-capable NIC with a bandwidth of 100 gigabits per second. Next is the NVM, which in this case is an Intel Optane PM. A few things to note about it. It provides a DRAM-like memory interface, which allows the CPU to use load and store and non-temporal store operations to read and write to it. The persistent section of this figure shows an exploded view of the NVM. Data is stored in NVM 3D X-point DIMMs, and the X controller transforms read-write requests from the processor or PCIe bus into read-write requests to the 3D X-point DIMM. The paper points out two important features of the X control. Requests are received by the X control in cache line granularity, which is 64 bytes. This is also the access granularity of the CPU and PCIe bus. And it goes from the X buffer to the XP line, which has a 256 byte granularity. The X controller also has a small write combining buffer, which is the X buffer you see in the figure. This merges adjacent cache line writes into one XP line write. And then the last thing to note regarding the NVM is that it has asymmetric performance features. Its read is much faster than its write at 320 gigabits per second versus the 100 gigabits per second. And sequential write has a higher bandwidth than random write due to the X buffer. And lastly, the two communicate, the two being NVM and the RDMA capable NIC, communicate via the PCIe bus. All right, so the study focuses on one-sided and two-sided RDMA primitives to interact with the Optane PM NVM. One-sided primitives communicate via PCIe read-write transactions. These can be seen here on the left, where sends go directly to the NVM on the server side. Two-sided primitives utilize the server CPU to read-write the NVM, which can be seen on the right, where sends go to the server CPU before being stored in the NVM. Note that two-sided also has the option to utilize PCIe read-write transactions, but aside from being briefly mentioned in the footnotes, the authors don't really mention it again when speaking to the performance optimization specific to two-sided primitives. They do mention that they don't show it in this figure because it mimics that of the one-sided primitives, but I still would have expected different performance characteristics, but maybe that isn't the case. Regarding the testbed, their testbed consists of one server and 5 clients. The server has two Intel Xeon Gold 5215M 10-core processors with 384 gigabytes of DRAM. 2 ConnectX-5 InfiniBand RDMA-enabled NICs, and one 1.5 terabyte NVM comprised of 12 Optane DIMMs. The client has two Intel Xeon E5 2650V4 12-core processors with 120 gigabytes of DRAM, and similar to the server, has two ConnectX-4 RDMA-enabled NICs. So as mentioned earlier, the author states that the focus of the paper is on remote write, wherein the client issues write requests to the server NVM using either one-sided or two-sided RDMA. The authors found that the remote read performance was close to that of DRAM for large payloads, and that the throughput degradation seen for smaller payloads was a factor of the CPU having a much higher read latency when reading NVM compared to DRAM. It was for these reasons that the authors concluded that NVM couldn't be a bottleneck for reads. Additionally, it has a much higher read bandwidth than the RNIC at 320 gigabits per second versus the 100 gigabits per second. These charts in figures 4 and 5 are intended to demonstrate that. Throughput and bandwidth for one-sided reads on the left and two-sided on the right. And so you can kind of see those. They kind of trend somewhat similarly to DRAM. Regarding the write performance, when comparing the use of NVM to DRAM, while noting that the NVM write bandwidth is the same as the RNIC bandwidth at 100 gigabits per second, you can see that there is a lot more room for optimization. The author illustrated this by including a line in these charts showing the improvements gained by implementing their optimizations. So we can see NVM's kind of at the bottom here, and then when introducing their optimizations, you can see the jump in performance. I thought it was pretty interesting that with two-sided writes, it gets quite near to DRAM with their optimizations. And then two-sided writes, they also introduced a limit line, which this is just measured from the server directly returning to the client without a payload. So effectively the round trip delay resulting from issuing requests. These are the optimizations used to achieve the improved performance and write throughput and bandwidth. They're broken down into three categories, which I've kind of labeled off here. Configuration, access patterns, and RDMA-Aware Optimizations. Of these, H1 through H5 came from existing studies. H6 to H8 are new optimizations introduced by the authors and were implemented to complement H4 and H5 after some drawbacks were discovered for smaller payload sizes. And H9 is a known RDMA optimization used to minimize the number of requests needed to confirm one-sided persistent writes via a technique called doorbell batching. On the following slides, we'll step through each of these hints, looking at the improvements stemming from each of them as detailed in the paper. So first off, H1 is to avoid cross-socket NVM access. The Yang et al. Study this hint came from found that NVM write bandwidth of a socket could be halved from other sockets since the RNIC leverages its attached socket to access NVM from another socket. This can be avoided by attaching an RNIC per socket and treating each one as a logical node in a cluster. Improvements from doing this can be seen in figures 8 and 9, where the 16-byte one-sided write throughput and the 2-kilobyte two-sided write bandwidth doubled after applying this optimization. I put arrows in the figures because I felt that some of the colors were a bit difficult to differentiate. Hopefully this was helpful. The red arrow points to base NVM performance, and the green arrow points to the NVM with H1 optimization. And then you can further see some of the improvements from applying the other optimizations in each category. H2 is to limit concurrent access to a single NVM DIMM for two-sided RDMA. Another observation from Yang et al. Was that the CPU fails to scale up alongside concurrent writes to a single NVM DIMM. This impacts two-sided RDMA because it relies on the CPU to perform the writes. A 37% bandwidth drop can be seen in figure 10A using 20 threads when compared to the performance of a single thread. However, looking at figure 10B, one-sided RDMA writes did not appear to suffer from the same issue, as its bandwidth seems to scale well with the increased number of concurrent writes. So in figure A here, you can kind of see that the two-sided RDMA writes and the CPU writes trend downward together as the number of server threads increase versus the single NVM DIMM limit. And then on the right, one-sided RDMA writes kind of scale constantly with the number of clients. H3 is to disable DDIO, and that if DDIO must be enabled to use two-sided RDMA for large writes. DDIO is data direct IO. This was found to have a significant impact on performance for one-sided RDMA and NVM writes for large payloads, and as such, it was deemed an important configuration for RDMA NVM systems. Figure 11A shows that only half of the peak NVM write bandwidth is achieved for large payloads when DDIO is enabled, in contrast to almost reaching peak bandwidth when it is disabled. Peak bandwidth here is just being the bandwidth limit of the RNIC and the NVM at 100 gigabits per second. To provide some explanation into what's occurring here, the DDIO-enabled RDMA writes get written to the last level cache on the server CPU, where it is randomly evicted to the NVM. Random writes to NVM cannot saturate the NVM bandwidth because NVM has less chance to merge adjacent writes to avoid write amplification. When disabled, writes bypass the CPU cache and go directly, and more importantly, sequentially to the NVM. This is illustrated in figure 12A on the far right, with data from figure 11B to show the impact of DDIO has to write amplification for one-sided RDMA writes. So you can see in figure 12A, when it is enabled, goes to the L3 cache and then randomly over to the NVM, versus disabled, going directly via PCIe to the NVM. And then the write amplification. So with a baseline of 100%, when it's disabled, enabling it jumping almost to 200% as a result. That being said, disabling DDIO does impact the cache locality for other DMA data. This had the effect of degrading two-sided RDMA performance as it makes use of the CPU cache. Therefore, the authors added an extension to the optimization stating that if DDIO must be enabled, two-sided RDMA should be used for large NVM writes. Moving on to access pattern optimizations, H4 and H5 also came from other studies, H4 being to use NT-store instead of store for large writes, taking advantage of the Optane PM's DRAM interface to write directly to the NVM device, thus bypassing the CPU cache, and H5 being to use the XP line granularity for writes, which if you recall is 256 bytes. The authors discovered that while H5 did offer improvements, they were not optimal for small payloads due to the resulting network amplification. The authors observed that the CPU and RNIC generated an extra read request to NVM if the payload of the write request did not fit their access granularities. These were the 64 bytes for the cache line and PCIe data words. When they don't fit, writes are performed in a read modify write pattern to avoid overwriting the original content. They mentioned that to fully utilize the NVM bandwidth, they would need to avoid sending unnecessary read requests. And it's based off this observation that they proposed H6, 7, and 8 to complement 4 and 5 from the other study. So regarding H6 and 7, H6 states that for one-sided RDMA, use the PCIe data word granularity when the payload is smaller than the XP line. And H7 states that for two-sided RDMA, use the cache line granularity with NT-store when the payload is smaller than the XP line. If you recall, one-sided RDMA bypasses the CPU using the PCIe bus to communicate with NVM, whereas two-sided RDMA use the CPU to communicate with NVM. Though the granularities are similar in this case, they could be different when using different hardware components. And as mentioned earlier, the paper didn't say that two-sided could use the PCIe to communicate directly with the NVM device. But other than that brief footnote, they didn't really bring this up again. So I don't know if that could potentially have changes or mean something different for these optimizations. Figure 13A on the top and B on the bottom show the read-write ratio for one-sided and two-sided RDMA writes respectively. You can see for both that when write is aligned with and padded to its respective granularity, the read-write ratio is 0. The exception being for two-sided writes, where NT-store also needs to be used. This is because using store resulted in the CPU performing an NVM read to prefetch the cache line. Lastly, H8 is to use less atomic operations with NVM. This stemmed from H6 and H7, where it was found that the read modify write access pattern was not very friendly to NVM. Because atomic operations tend to follow a similar pattern, it was recommended by the authors to move data for atomic operations away from NVM and into DRAM whenever possible. And then the last optimization hint is an RDMA-Aware Optimization. It is to utilize doorbell batching for one-sided persistent RDMA writes. In order to confirm that one-sided writes were persisted, a follow-up read request would need to be made for the data. This is generally done with 2 independent requests. However, with doorbell batching, these 2 requests and the responses can be delivered and received in a single request, thus saving the client the round-trip time needed for the second one. And then moving on to the improved system design section. In this section, they talk about the improvements they made to existing systems. The first of which is the DRTM plus H, which is a distributed transactional system designed for RDMA and NVM. They evaluated this system using the TPC, C, NO, and small bank benchmarks. And the second is a distributed file system called Octopus, designed for RDMA and NVM. They evaluated this system using the DDIO benchmark that they found in the initial Octopus paper. So figure 14A and B show the result from the TBCC, NO, and small bank benchmarks respectively. Like other charts in the paper, they show the incremental improvements or detriments of applying the optimizations in steps with vanilla NVM being the base, and each step moving performance closer to that of the use of DRAM. What I found interesting in these charts is that you can see the significant performance improvement of applying optimizations 1 through 8, and then a noticeable drawback when they added persistence checks, which stemmed from the additional requests needed to confirm persistence, and then the application of H9, which kind of brought it back in line with the pre-persistent performance. I also kind of liked how the charts were a bit additive, so you can kind of see the effects of all the changes. Additionally, for DRTM plus H, the authors provided charts to allow readers to see the additive improvements of each individual optimization step for each of the benchmarks. Here you can see the dip in performance when persistence checks were added and the slight improvement when H9 was implemented. Another interesting tidbit noted by the authors is that while several optimizations provide benefits to both workloads, some have a negative impact. For example, small bank lost 15% throughput when H3 was applied because H3 is only beneficial when the application is bottlenecked by the NVM bandwidth. And it did not appear to be the case with that workload. And then lastly, the results from benchmarking Octopus are in figure 17A and B. It's interesting to see how close the authors were to mimicking the performance of DRAM when implementing NVM with their optimizations. Again, we see a significant improvement when H1 through 8 are implemented, and then a drawback when persistence checks are added, and a slight improvement when H9 is added. And that's it. Thank you for listening. The paper mentioned that many of the other studies were based on RDMA with emulated NVM. So I felt in this paper it was kind of nice to see empirically how well the optimizations performed with actual NVM hardware, as well as the additional optimizations that came from working specifically with the components used in the study. So I thought that was some pretty cool stuff. And thank you for the opportunity to present.